Gravity is not the only type of potential energy. Another one is elastic potential energy, the potential work that is stored in a stretched rubber band before you let it go, or a spring. Just like how gravitational potential energy can be converted into kinetic energy if we let an object fall, elastic potential energy can be converted into kinetic energy of the elastic body as it returns to its original shape and size after being deformed. Springs are great case studies for elastic potential energy, so prepare to see a lot of springs in your near future. We can essentially represent any elastic type situation with a spring, just like we approximate any body with mass as a box. So if you imagine compressing or stretching a spring, it gets harder and harder as you compress or stretch it further and further. Maybe for smaller springs you can completely overpower it, but imagine a spring that you can easily compress a little bit, but it's very difficult to compress completely. To keep an ideal spring stretched by a distance x, we exert a force based on its position, F equals kx, where k is called the spring constant of the spring. It's different for each spring. The observation that force is directly proportional to the elongations of a spring or rubber band, for elongations that are not too great, is known as Hooke's law. It really shouldn't be called a law because it's just a statement about a specific device and not a fundamental level of law of nature, but this is what people call it, and so here we are. You can see how this provides a stored potential energy based on the spring's position, in the same way gravity provides a stored potential energy based on height. We'll proceed in the same way as we did for gravity to see how this elastic potential energy works with our energy approach. So say we have a spring like I've drawn here. We've defined the x-axis as the level ground here, and x equals 0 at this spot where the spring is neither stretched nor compressed. It's the natural resting state of the spring. And we have this box that's attached to the spring, and the spring is attached to the wall on the other end here. So this does not move. So since the force as a function of x scales linearly with x and is not constant, we can draw a graph of its force versus displacement. And it would look something like this. So if we had a graph of force as a function of x on the y-axis, and then its position x on the x-axis, so this is f of x. It might look something, since it's linear, it might look something like this. And this distance here, from here to here, this is k times x. And this distance here to here is x. Yeah. That's x, right? And we'll come to a more intuitive understanding of it, but the area under this is going to be the work. So if we modify this a little bit more specifically, if we have this same plot of the function, or the force with respect to x on the y-axis, x on the x-axis, just the same. But this time we label, so this is x equals 0, so that's the origin. We'll label that x1, and this x2 here. And we have the same, I'll use this code here. We have the same linear force right? But we want to know from from x1 to x2. And so it's going to be this area under here between x1 and x2 that we care about. Okay. So the work done on a spring to stretch it from x1 to x2 is what we're talking about. And that's going to be equal to, so the work done is going to be equal to the integral from x1 to x2, right? Because work is force through a distance, force through a distance. And so you're multiplying force times distance, so you're getting the area under the curve, right? So in this case, since it's changing, we can't just take two sides and multiply like a box. We have this function that's changing, and so we have to use an integral. So f(x) dx, to find the area, and that is from x1 to x2, that's f(x), oops, kx, the spring constant k times x, that's what the force is equal to for a spring, dx. And so if we integrate that, we get that the work is equal to 1/2 kx2 squared minus 1/2 kx1 squared. Kind of looks familiar. It takes on the same form as kinetic energy, but this time we have this k, spring constant, and it's different. But again, we have this scenario where we have work. If the work from the spring is the only work being done on the whole system, then this would be the total work is equal to the difference in two quantities here. Right? And so just like we did for kinetic, and just like we did for gravitational potential, we're going to define these quantities as something. And we're going to define it as a potential energy, but it's not U-grav, like before, because it's not gravitational. It's elastic. So I'm going to say UL for elastic is equal to that quantity 1/2 kx squared. So that is elastic potential energy for things like a spring. And so thus we can express the work done on a block by the elastic force in terms of the change in elastic potential energy. So we have work elastic, because that's the only thing being done on the block, like we were saying before. It's U elastic 1 minus U elastic 2, which is equal to the inverse, or the negative of delta U elastic. All right, so let's go back to our picture of the spring here. While I hold this in my hand. Let's see, how do I do this? So, let's get this up on the screen. So for our spring, as we stretch the spring, it does negative work on the block, because we're pulling the block this way, but the spring is exerting a force on the block that way. It does not want to be stretched, and so it's doing negative work. as we let the block go from its stretched position, then the block would be going this way, and it's still in its stretched position. And so it would be, the spring would be doing positive work, because the spring is still pulling it back towards its x equals 0 point, but the block is out here, and so it's going to be doing positive work. And if we compress the spring, so if the box is pushed this way, then we're pushing the block this way, and it's traveling that way, but the spring is exerting a force that way, so it's doing negative work. But as we let it go, then the spring is doing positive work on the block. So I'll get back to the bottom here. So one of the things that you saw me do at the beginning of this video with the diagram I drew turns out to be pretty important, which is to set the x equals 0 point at the natural resting point of the spring. So that's one of the things that has to be done. It doesn't actually have to be, but it really makes it easier if you do that, to the point that you really, really should. So on our diagram, right, the block is here. This is the natural resting point, x equals 0. If it's stretched, we've stretched it out more, very stretched out spring, this is some x equals something positive, and if it's more compressed, then x would equal something negative. It's really compressed. And this is x equals something negative. So the natural resting point of the spring should be set at x equals 0. And so the reason for that is because the spring's natural resting position is the position where the spring's elastic potential energy and the force that it exerts are both 0. So if you have a spring sitting, if you have a box sitting attached to a spring, I'll do this for contrast. Natural resting point, yeah? The spring is not doing any, exerting any force, and so the force that a spring exerts is kx, right? So it's dependent on its position. And so you want the natural resting point here to be when force equals 0. And so you want x to equal 0, and so the total force to be 0. That's why. If you put x equals 0 here, well then this is some positive thing, and the spring is not actually exerting a force, but according to how you define your axes, it is exerting a force. And so you must set x equals 0 to be at the natural resting point of the spring. Or you would have to do some sort of you would have to redefine this as k times x plus or minus something, right? But don't even worry about that. Just set the set the x equals 0 point at the point where the spring is not stretched or compressed. So if you remember, the work energy theorem stated that the total work is equal to the difference in kinetic energy, K2 minus K1. That's the work energy theorem. We've encountered this. And that's true no matter what kind of forces are acting on the body. So this applies to elastic scenario as well. So thus, if elastic force is the only force that does work on the body, then, like we said before, the work total is equal to the work elastic, which is equal to U elastic 1 minus U elastic 2. I know we already wrote something similar to this, but this builds up to something new. So the work energy theorem, if you put those two together, is then equal to K1 plus U elastic 1 is equal to K2 plus U elastic 2. Right? So this is identical form to what we came across with gravitational potential energy. You literally have something exactly like this written in your notes, except for instead of U sub L, it's U sub grav, right? So it just means the total kinetic and potential in the form of elastic potential energy there is in this state 1 or point 1, that's going to be equal to the total kinetic plus the total elastic potential in this moment or state or point 2 in some scenario that you're analyzing. It's just trading between kinetic and potential, right? There may have been no trades made even. So to write this out fully, we know kinetic, that's 1/2 mv1 squared, and now our new elastic potential is 1/2 kx1 squared equals 1/2 mv2 squared plus 1/2 kx2 squared. So they're very similar looking. 1/2 mv squared and 1/2 kx squared, but they refer to two completely different things. Right? This is kinetic, and this is elastic potential. Right? So if you have a scenario like the block in the spring that I drew up there, and you're not considering, it's not moving up and down, so gravity is not doing any work on the block, and you're not considering friction, you have a system that has some kinetic energy at various points, and it has elastic potential at various points, and that is it, nothing else. And so in that case, we say the total mechanical energy is conserved, and an ideal spring provides a conservative force. And that's the same with gravity. Gravity is a conservative force. We'll talk about that more later. So you say, we've analyzed some more complicated things than just these little isolated systems. You're giving us all these energy analysis tools, but they seem to be quite limited because last video we talked about only things that related to when gravity is the only thing doing work. And this one we're talking about so far only things when elastic potential energy is the only thing doing work. Well, what if you have multiple things? What if you have things going on like this, where you have some sort of a spring on a block that's going up and down, right? Down a ramp and such. What then? Shouldn't we be able to deal with stuff like that when there's multiple things going on? Yeah, definitely. So how about if we have both gravity and elastic, and maybe some other work altogether, like friction, right, being done by non-conservative forces, which would be like friction. So let's throw it all together and find the work energy theorem that is valid in all cases. It's always nice to have something that applies always, no matter what, instead of all these very specific cases. So we can get there now. If we have elastic, gravitational, and some other work going on, then the work energy theorem says that the work total is equal to the work from all of those things. U grav plus W grav, work from gravity, the work done by the elastic force, plus the work done by whatever else. We were thinking friction. There could be other things also. Work is just anything that exerts a force in the direction of motion, right? The work is anything, force through some displacement. So it could be friction. It could be you pushing on a block, something like this. So all of that is going to be equal to the difference in kinetic energy. That's the work energy theorem. So the work from gravity specifically is going to be U grav 1 minus U grav 2. And the work from elastic is going to be equal to U elastic 1 minus U elastic 2. Right? So we can start to fill these things in. So if we rewrite this top equation in gold, filling in some details, then what we have is U grav 1, and we're going to rearrange a little bit, plus U elastic 1, plus work done by other forces, whatever they may be, there may be multiple, is equal to, plus the kinetic, I'll write it over here, plus the kinetic energy, plus K1, is equal to K2 plus U grav 2 plus U elastic 2. So that's everything. That is everything. And since gravitational potential and elastic potential really fall into the same class of potential, which we denote with a U, what we can do is just say K1 plus U1 plus work other is equal to K2 plus U2, and that's it. So this is the one to box in. This is the completely general energy statement. The kinetic energy of an object plus the potential energy from the object within the system that it's in, so by position, plus any other work that's happening, is equal to the kinetic energy plus the potential energy in the object system in some later point. And so the way to interpret this, is the work done by all forces other than the gravitational force or elastic force equals the change in the total mechanical energy of the system. Right? So remember, total mechanical energy, E, is equal to the kinetic plus the potential. Right? So this work other determines whatever change in E. Right? So work other equals delta E. That's one way to think about this. Right? So if there's some sort of work other contributing, then it's adding or subtracting to the total mechanical energy of the system. If we want to write out this, I'm going to just make the same room so I can write just below it. But if we want to write out more explicitly what's going on here, we can say where U is equal to U grav plus U elastic, right? And U grav is equal to mgy, and U elastic is equal to 1/2 kx squared. All right, so now the next video is going to be dedicated to 3 examples that are going to be using this, putting it all together. You can see how you might not have everything, and so if there's no gravitational potential going on, then you don't have any U grav, and so you only have to consider the elastic. Or there might be other ones, like we've seen before, where there is no U elastic, and you only have to consider U grav. And there's some even more basic where there's none, right? So there's no potential energy going on, or both, right? So there's all kinds of different combinations, and so we're gonna throw it all in there and slowly build up 1, 2, and 3 examples next video of using this great energy statement here to solve some problems.